We'll see how this goes. So, uh, the main thing that I wanted to start us talking about this time was making sure we understand that we're working on eigenvalue problems and the kind of restrictions that we've already had and the restrictions that we need to introduce in order to have really well-defined systems. Right? So this is a generic eigenvalue problem. And we already said that we've got some restrictions on psi. We said, hey, in order for this to work, psi needs to be well-behaved. The reason that we need it to be well-behaved is because we've defined psi. In particular, we said the integral of psi star psi d tau is going to be essentially a total probability. If we're doing this over all space. We also could do it over a restricted amount of space to say, oh, I only want to know the probability in a small piece of space. But we can also do it over all space. And so we needed something that could be integrated. That is to say, we needed it to be finite, single-valued, smooth, and continuous. We needed all of those things to be true. We also, and this comes out of the postulates of quantum mechanics. This is our first postulate of quantum mechanics, the fact that essentially psi squared, absolute value of psi squared, or psi star psi tau, is a probability distribution. Psi is going to define everything about our system. That's all from the first postulate. The fact that we're doing an eigenvalue problem is coming out of what I call the third postulate. And there's another thing. That A is supposed to be something that we can measure. And if it's something we can measure, we need this to be real. Right? And we know from the work we did last time that if this is some differential equation, this could end up having complex wave functions. Part of the reason we're doing psi star psi is to guarantee that our probability is real. That's why we're doing the integral in this way using psi star and psi. If we want to guarantee that A is real, essentially what we're saying is that the value A, if we took its complex conjugate, would also be equal to A. Right? So if I take the complex conjugate, I just get the same thing back. The only way that happens if there's no imaginary parts. It's completely real. So we want to guarantee that this is true. We want to guarantee that we have real eigenvalues. Another way we can look at this, instead of if we didn't have specific eigenvalues, we could instead look at the average eigenvalues and say that the average of the complex conjugate of the average eigenvalue also has to be equal to the average eigenvalue. This is guaranteeing real eigenvalues to our problem. This is guaranteeing that we're going to get something that's measurable in real space, which we have to have if we want something that's measurable. We can't measure in complex space. Now, in order for this to be true, we're going to end up with another integral that defines our average A value. Again, I'm using A as like any operator. It's my generic operator. If I take the integral of psi star and I put that operator in between, so A is going to operate on psi. That's going to give me A psi back. And if I integrate over all space, I'm integrating probability over value. That's going to give me my average A. I'm going to simplify this a bit so I have a little more space. I'm just going to say all. Now, if I want the complex conjugate of that to be true, I'm also going to have this. We're not going to do much to prove when these things are true, right? I'm showing this to you, and the operators, the situations where this is true, where these two things are equal to each other, that's a special category of operators. That's going to happen when we have something called a Hermitian operator. So we're going to be doing, when we look at our observables and we have these analogies from classical mechanics, whether we're looking at translational motion, vibrational motion, any other potential, we're going to have momentum, position. We're going to have some operator that is going to be the analogy in quantum mechanics. Our classical observables are going to have a quantum mechanical operator analogy. Not only is it an operator, but it has to be a Hermitian operator to guarantee that we get some real measurable value. In terms of what I want you to know, something I'll point out with the math we did last time, we looked at d by dx, and that one, it turns out, is not Hermitian. So d by dx is actually a kind of bad thing to use as an operator. We can still do eigenvalue problems with d by dx. We did eigenvalue problems with d by dx, but we're not going to have this guarantee that our average values are going to be real. So it's not going to be a good operator using quantum mechanics. And in fact, the one that we use, and we would think to use this when we're talking about momentum, the change with position, the one that we use for momentum, if we're looking at the x position, is IH bar d by dx. Right? That I out front is going to give rise to the fact that we end up getting this statement to be true. If that's not obvious to you, the textbook goes through a problem like this. I'm not going to ask you in this class to prove an operator is Hermitian. I'm not going to do that. So you're not going to actually have to apply this. But you should know that we have a restriction on our operator. And that restriction is essentially to guarantee that we have real values. So that's going to affect this. Right? That's going to put limits on our operators. Not like integral limits, but it restricts what our operators are allowed to be. So d by dx doesn't work out, but IH bar d by dx does. If you're like, whoa, I want to see the proof for that. Textbook does a problem. The short of it is you have to do integration by parts to get this to make sense. And like I said, I'm not going to ask us to do that, but it's important to realize we're going to be using Hermitian operators. There's going to be an extra benefit of Hermitian operators as well. This is going to be actually a really huge benefit for us. The size, the wave functions associated with Hermitian operators are going to be orthogonal. That is to say, if you think back to our example, we had a situation where we looked at a cosine term, a sine term. Those were both solutions to our problem. If we looked at those, they're going to have the property, if I'm looking at two, and we're going to do some examples with actual numbers to look at this in class. So if you're like, wow, that's a lot of symbols, I don't get it yet. We're going to do this with actual functions and real math in just a moment. So we're going to have one function times the other function if n does not equal m. That is to say, if I'm looking at two different functions, both these functions have to be eigenfunctions for a Hermitian operator, but those two functions will now have an integral of 0. Why is this good news for us? Well, this means that there's going to be a lot of places where we're doing a bunch of integrals, and as long as we can recognize the fact that both the functions are eigenfunctions of a Hermitian operator, we're already going to know whether the integral is 0 or not. That's going to be really useful for us. Right? We're going to be able to show whether things are 0 without actually having to do the integrals, which is going to save us a bunch of time. It's a good thing. So, and we're going to talk more about that in just a moment. So let's get to any questions about that? So we're remembering that we can get total probabilities, we can get average values, and now we've got this new thing. That should all be review. Our new thing is Hermitian operators, and they satisfy this where these two equations would be equal to each other. So let's talk about an interesting system that we can actually solve. That is going to be an eigenvalue problem that uses all of this information. If we want to think about the easiest place to start in quantum mechanics, in solving any problem in any physics, chemistry class, we're going to think about the simplest thing. We're going to think about a particle just moving through space. So if we have a particle that's just moving through space, we can say that the only thing associated with that, our Hamiltonian, which is going to be kinetic energy operator plus potential energy operator. When we write this down, we can write down our kinetic energy equals p hat squared over 2m. Remember, this is the kinetic energy. If that didn't have the hat, that's the kinetic energy classically. Since we're doing quantum mechanics, we put a hat on there. And then our potential energy is going to be a v hat. And it's just some v. For each system we look at, we have to define what this v is. We have to know what v is. And that's going to be the thing that changes in our problem with each problem we do. Now, we're going to, again, just like we were doing before, restrict ourselves to just one dimension. So I'm going to call this px, and I'm going to look at a vx. If I'm using the px, this Hermitian operator for momentum, I can go ahead and plug that in here. And if I'm looking at a particle that's just moving freely through space, if we're looking at a particle that's moving freely through space, there is no potential acting on it. So we're going to get our Hamiltonian. It's going to be a negative h bar squared over 2m d by dx squared plus 0. You don't really need to put the plus 0, of course, but that's just because the potential is 0 in this case. V of x equals 0, so I just have that. Now, we can go ahead and say, okay, I want to set this up where I can find the energy. I'm looking at total energy. I want to make sure energy is conserved. That's why we're using the Hamiltonian. So I'm going to set up my eigenvalue problem specific to this, and that's going to be h psi equals e psi. Right? I'm going to have my Hamiltonian operate on some wave function. I'm going to get the energy back out plus that times that wave function. Yeah?
In the first line, when you look at Hamiltonian, is that also operator?
Oh, yes, yes, sorry. When we get later into quantum mechanics, we get really lazy about the hats because everything's operators, but I should be explicit. Yes, that's an operator as well. We should be careful and explicit for now. Yeah?
When you plugged in the momentum, where did I go?
I squared gives us the negative out front. So I'm going to go ahead, plug in the Hamiltonian. We don't know what the wave functions are for this yet, but we're going to go ahead and set this up like a differential equation. I'm going to have negative h bar squared over 2m d by dx squared on psi is equal to e psi. I'm going to rearrange this just a little bit. And then you might see a problem that we did last time. I can't remember. Oh, now I'm forgetting what I did last time. But we can already guess what the psi's are going to be related to. I'm going to multiply by 2m over h bar, bring the e psi over, and I'm going to get d by dx squared psi. Well, got to make sure I do this right. Plus 2me on h bar squared, h bar, psi equals 0. Right, so I multiplied by the negative 2, then brought this over. I'm going to go ahead and call this whole thing k squared is equal to 2me over h bar squared. And then I'm going to go ahead, switch that to k squared. Do you remember doing this problem? It turns out we solved this equation last time, right? The reason I put a plus instead of a minus wasn't because I just randomly clicked the plus. It was because I was setting us up to do the Schrodinger equation for a free particle. That was intentional on my part. So we've already solved this. We can, and to be clear, there are ways where we can solve differential equations explicitly by doing power series expansions. 1 through 5, how much do you love power series expansions? That's a lot of zeros and ones. Oh, man. Okay. I'm going to do a quick aside because I absolutely love power series expansions. And the reason I love it is because it makes so much physical sense. But when I learned it in a math class, I was like, this is pointless. Why are we doing this? We're just making more terms. But there's a reason that we have power series expansions. And I'll do 2 examples of why. Here's example 1. Kind of generically, let's say I have a curve. And I wanted to describe that curve with as many simple lines as possible. How many lines would I need? 2, 3, infinity. Technically, if I wanted to get the slope at every point, I would need an infinite number of lines to represent this. So I would need an infinite series expansion. However, if I look at this and I just expand it to 2 terms, I could say, you know what? If I just draw a triangle like that, that's pretty close. So this would be like expanding in terms of doing a power series expansion in 2 terms. If I wanted to be a little bit better, I could do a power series expansion in 3 terms. Right? I got 3 lines, and that's going to be a pretty good approximation of my curve. Technically, to get it absolutely correct, I'd need an infinite number of terms. But this is going to get me pretty close. Now, the one that we're going to use most often in this class is e to the, I'm going to go ahead and say e to the ax. Does anybody remember the power series expansion for e to the ax? Look it up real quick. Talk to your neighbor. While you look that up, I'm going to draw and I'm trying to, and the reason I'm having you look it up is because I want to make sure I'm remembering it correctly. I forgot to write it down in my notes. I know it starts with a 1 plus. There's a 1 plus x.
Yeah.
This would be if we did the power series. Well, keep the power series expansion up for a moment. I'm going to need your help. If we just did the power series expansion in terms of 1 term, and we just said e to the ax is equal to 1, I would get a line that's like this if I just did 1 term. That's okay if I'm really, really, really close to 0, actually. But that's not always going to be the case. So then I want to include a second term. I'm going to have 1 plus x. So now, if I draw the line for 1 plus x, I'm going to have a straight line that kind of goes like that. You know, it's plus 1, and then it's just a straight line. That's better than 1 term. Right? I'm actually closer to the answer than I was before. Now, if I remember correctly, it's plus x squared over 2 factorial. Which is just 2. In that case, if I looked at these 3 terms, 1 plus x squared, I'm going to get something that kind of does that. I'm actually getting pretty close to matching an exponential with just 3 terms, and I might have exaggerated coming out a little bit too far. I know that the exponential rises faster than x squared, so I know it should be like that to some degree. But notice, with 3 terms, I'm actually pretty close to modeling an exponential now. And then I could add a 4th term. The 4th term would be x cubed over 6. This is all expanding about 0. And then I would have to, and doing these 3 together, I can't think how to plot that. I should have brought like a MATLAB thing to plot these for us. But I'm going to get closer to an exponential. So what a power series expansion actually does is let us approximate the curve by just adding polynomials together, right? 1 plus x squared is going to get us a pretty good approximation of an exponential within some limits. Depending on how accurate we want to be, we'll keep a different number of terms. But this means I can actually start to model really complex things. And again, the textbook talked about this in section 7a for both the black body radiation and for the heat capacity at low temperatures. They did Taylor series expansions, these power series expansions, to simplify the exponential terms. And that's kind of why we always do it. You know, e to the a temperature doesn't make as much sense to me as 1 plus temperature squared. Right? This is going to be easier to understand in terms of a physical representation. It's also going to simplify our mathematics and allow us to take limits a little bit easier. This same type of idea is also how differential equations are actually solved. We're doing guessing check. That is to say, we're looking at this and we're saying, yeah, sine would work, cosine would work, e to the x would work, e to the ix would work. We're just looking at this and saying what things would work when we could be doing power series expansions. But that was a lot of people with 1s and 0s for power series expansions. I will tell you, they will come back. They are fantastic things that simplify our lives when we're actually applying them correctly. Because we never actually take them to infinity. We take them to like 2 or 3 terms. My favorites, every once in a while you get like a physical proof where they're like, we're just going to take the first term. And they just like take the 1. And we could do that. If we were really close to 0, all this stuff is going to be 0. And you're just going to say e to the ax, where x is almost 0, is just 1. And there are every once in a while there's a proof where they say, oh, the exponential is equal to 1. We're not going to worry about it. So like these expansions are actually going to help us a lot throughout this class. Back to this stuff. So if you're not a huge fan of power expansions, they're actually really useful. Back to this stuff. So we looked at this last time when we said, hey, I know that if I'm looking at this, I'm going to have wave functions. I'm going to have some possible wave functions. I could have psi is a cosine kx. I could have sine kx. I could have e to the I kx, or I could have e to the minus I kx. Oh, actually, I'm going to do another power as well. We could do another power series expansion thing right now. So, what if I told you, let me change this to ors like I had before. Right? What if I told you that cosine and sine were both e to the I kx's? These were all related to each other. Because they are. So if we did the power series expansion of e to the I kx, and we did the power series expansion of sine kx, and we did the power series expansion of cosine kx, we would find out that e to the I kx is equal to cosine kx plus I sine kx. If we did these power series expansions, if I power series expanded this, it would be equal to those 2 power series expansions. That's the way I like to prove. This is called the Euler decomposition. And I like to prove the Euler decomposition by doing power series expansions. Your textbook also goes over how you get from e to the ikx to cosine and sine. They do it through complex plotting. So if this is real and this is imaginary, that angle is kx. You can do a real and imaginary projection. And essentially, as kx changes, you can go from completely real, which would be like cosine kx if that was like cosine kx equals 1. It would be completely real. And if you go to sine kx equals 1, then you'd be in completely imaginary. And then so you can see how the cosine sine part relate to an e to the ikx through that as well, where this thing would be like an e to the ikx. There's another way your textbook goes through it with a little bit more detail. I like the power series explanation. Because the power series explanation, these two things, and I should put the I here, these two things add up to the e to the ikx power series expansion. And this, if we remember just a little bit, power series expansions, cosine is, I'm looking for an E word, even, right? It goes x squared, x to the 4th, x to the 6th, right? This one's going to be even. Sine kx is odd. It goes 1, x. No, oh, sorry. Cosine is 1, x squared, because 1 is x to the 0. 1, x squared, x to the 4th. Sine is x, x cubed, x to the 5th, so on and so forth. You add those two together, and you get your power series expansion of 1, x, x squared, so on and so forth. So you can actually show this. What this lets us do is it's going to allow us to flip which kind of solution we're looking at. I erased my eyes. It's going to allow us to flip whether we want to be looking at cosines and sines or if we want to be looking at exponentials, because they're actually going to be equivalent to each other. Sometimes one is more mathematically easier to use than the other. So let's go ahead and look at that. When we're looking at a free particle, wait, let me do one other thing first. Let's leave that there for fun. We're going to use that again. So when we look at this, and we can say now that we've got some wave functions, we can start to think about what the wave functions represent. And what we realize is that these possible answers are eigenfunctions of the Hamiltonian. That is to say, they are eigenfunctions of energy. That does not necessarily mean they are eigenfunctions of position or of momentum. And if I looked at momentum, which we all know now is IH bar d by dx, if I looked at momentum on cosine kx, I would get IH bar, hold on. I'd get IH bar k sine kx. Take the derivative once. Am I off by a negative sign? Cosine goes to sine. Either way, is it negative? Yes. Negative, okay. Off by a negative sign. Always check my negative signs. Biggest mistake we make in quantum mechanics is missing, honestly, is missing negative signs. They're really important. Don't forget your negative signs. But the main point here is this is not an eigenfunction, right? I go from cosine to sine. I've got a hat psi equals a phi. I've got some different function. So when I look at this, cosine is not an eigenfunction of the momentum operator, because I get a different function back. Instead, let's consider, and the same thing would be true for sine kx, but the e to the ikx would work out better. If I do p hat on e to the ikx, I would get I squared h bar e to the ikx. Making sure I'm doing my math right. Double check me. Oh, I forgot something. What'd I forget? K, right? The K would come down as well with that I. I can look at this, and in this case, I've got e to the ikx, e to the ikx, and my eigenvalue. So in this case, e to the ikx is a eigenfunction of the momentum operator and of the energy operator. It's an eigenfunction of both. And I'd have a eigenvalue, negative h bar k. Essentially what this communicates is I've got a particle with a negative momentum. That is to say, the particle from wherever I'm looking, the particle is moving backwards away from it. If I do the same thing with e to the minus ikx, I'd get a particle moving forward. So I can look at this and I can say I can have a particle moving one direction or the other. And that's true for a free particle. None of these, so there's benefits in using e to the ikx instead of cosine kx in the case of a completely free particle. The problem is, when we're doing this, when we're using these, I'm going to want to leave this guy for us. Right? That's the thing we're solving today. The problem is, when I look at this, I say, okay, well, can I figure out some other values? What information can I get about the system still? I can get momentum. I've got eigenvalues for momentum. It can be moving either direction. I can get energies. My energy is going to be, where did I put it? Oh, my energies are going to be some values. They're going to have some values. But if I wanted to know the position, we can ask what other things we might want to know. We might want to know the average position. Now, since the position operator, x hat, is x times psi, you know, it's operating on the function, it's time psi, it turns out that it's really hard to find functions that are eigenfunctions of the position. There's only a few weird situations where we get eigenfunctions of the position. Does this mean we don't know where things are, that we can't measure where they are? No. What it means is we're restricted to looking at our average position, right? We're looking at these averages, these expectation values. So x is one thing that we might want to look at. X squared, so that way we can look at a deviation from the average. That's something we're going to look at. Average momentum, p squared, that's something else we might want to look at. And then the energy eigenvalues. All of those things are things we might want to look at. We can get expectation values for position and momentum. Sorry, for energy and momentum, we can get expectation values. For position, we have to do averages, and then we can talk about the deviation from our average using x squared average. But there's even a problem with that if we're looking at a particle over all space. So if I'm doing the average here, if I want to get x, I'm going to do an integral, right? I'm going to do an integral like this. Average x is going to be the integral over all space psi star x hat psi dx. I can even just replace that thing with x times psi, right? That's the x hat operator. Can we do this integral from negative infinity to positive infinity? No, right? If we try to do this integral from negative infinity to positive infinity, we're going to run into some trouble because of that x term. So what we do is instead of looking at all space, we instead start to look at restricted space. We look at finite space. We start limiting, instead of looking at this thing everywhere, we start limiting where we're looking. And this makes sense, right? How often do we actually care about a particle that exists in all space? Usually we're concerned about a particle next to an atom in a specific area. Or we're concerned about a particle in a molecule, like an electron across like a conjugated pi system, across some molecule. Right? We almost always have some restricted space we're looking at. So it's reasonable to say, actually, instead of all space, I'm going to restrict my space. And instead of doing the free particle, I'm going to change to doing the particle in a box. Now the particle in the box is going to look very similar to the free particle. For a particle in a box, v of x equals 0 from 0 to L. I've got some distance where I have no potential. And then I'm going to approximate. I'm going to say otherwise or v of x equals infinity. Now, of course, we never actually have an infinite potential, but we can have a relatively large potential compared to what we're looking at. If you look at a particle in an atom, you can say to get that particle completely away takes a huge amount of energy. That would be kind of like an infinite potential, roughly, but we're going to find that's not true in a couple of weeks. In this limit, I'm going to have d by dx squared of psi is equal to plus k squared psi is equal to 0. Or I'm going to have infinity. Essentially, either I've got this when I'm in this boundary, or I've got infinity. If I draw this, if I write something if I draw a picture of this in energy space, particle in a box is often abbreviated PIB. I would essentially, on my x-axis, I would have some x equal to 0, some x equal to L. My y-axis is energy. From x equals to 0, x equals to L, I'd have 0 energy. As soon as I get to 0, my energy skyrockets up to infinity. When I get to L, my energy skyrockets up to infinity. In order to have a particle existing out here, I would need a particle with infinite energy. Can I have a particle with infinite energy? Thumbs up for yes, thumbs down for no. No, of course not. So that means out here, psi is equal to 0. In here, psi is equal to something. And out here, psi is equal to 0. I've got these limits. Fortunately, we don't actually have a new problem to solve. Right? We've already solved this. Notice these two equations are actually the same thing. So I know that this psi question mark, this psi inside, is, I've got options. I could use the e to the ikx plus e to the minus ikx with some coefficients out front that I'd have to solve for, some a, b, where I'd have to solve for a to figure out how much of it is a particle moving in the negative direction, how much of it is a particle moving in the positive direction, but I could figure that out. Or I'm going to use different variables just so we don't get confused about which things we're looking at. Or I could look at some c sine kx, d cosine kx, where I have to solve for a, b, c, d if I'm going to be doing these like combination type answers. But we're going to be able to solve for those from the boundary conditions. So let's go ahead and apply some boundary conditions. And this is, again, where making choices actually makes our lives easier. The 0 boundary condition is pretty easy for both of them, but the L boundary condition is much easier for using sines and cosines. So for this case, I'm going to pick, and we know that these are equivalent through the thing I just erased. The Euler decomposition is going to tell us that we can relate these things to each other and they're actually equivalent to each other. So I'm just going to go ahead and I'm going to pick this one because I already know it's easier. I already know it's easier because I already did this problem getting ready for this lecture. But we can also do the other one. Maybe I'll put that on a homework assignment where you have to do the harder version. But let's go ahead and look at this. For my boundary conditions, I know I've got some restrictions on my wave function. It needs to be continuous. That means psi at 0 at that position has to be equal to 0, so because I've got a 0 outside the well. So I need it to be 0 there, so it's 0 on both sides of that condition. That's a pretty easy one to do. I'm going to have C sine of 0, D cosine of 0. What's sine of 0? 0. What's cosine of 0? We've solved for one of our coefficients. Turns out this cosine part doesn't actually exist. In order to have our boundary condition matched there, this D part has to be 0. And that makes sense because the cosine wave would be some non-zero value at this boundary. But we need it to be 0. So it turns out we can't have the cosine part. So we know D is equal to 0. Then we can go ahead and apply our other boundary condition, L. Psi of L, that's boundary condition 1. This is boundary condition 2. Psi of L is equal to 0, right? I have the same condition at this wall. I have 0 outside of here, so at this wall, I need the wave function to hit 0 so I can have that nice continuous wave function. So I know psi of L is equal to 0, which is going to be equal to C sine of KL plus, I already know this term is 0, so I'm just going to put plus 0. What are our options for making this term 0? Option 1? C is equal to 0. Yay, that would be great. Except that is what we call a trivial answer. You would essentially say wave function doesn't exist. Right? If the wave function doesn't exist, yeah, you don't have any energy. You're fine. Right? You're not doing anything. So picking C equals 0 is actually a bad choice. What's our other option? Let's ask it this way. When is sine equal to 0? 2 pi. Where else? 4 pi. What about pi? Pi. Pi, 2 pi, 3 pi, 4 pi, all the pi's. So I could just say KL equals n pi, where n equals 1 or 2 or 3 or 4 or whatever. Right? In that situation, this boundary condition would be met. So because I'm looking at a restricted space, I'm putting some restriction on my wave function. KL equals n pi. If I want to solve this for something that I can plug in, I would rearrange this and say K is equal to n pi over L. K equals n pi over L would give us our required thing. We'll come back to average position in just a moment. I'm not worried about the free particle anymore. We're moved on from that. Oh, I still wondered what that K was equal to. 2me over h bar squared. Am I right? Okay, good. Oh, that's weird. I've got two things that K is equal to now. I've got 2me over h bar squared, and I've got n pi over L. This means that because of this boundary condition, I've actually put some restriction on this energy that we have. I'm going to have n pi over L is equal to 2 me on h bar squared. A little bit of rearrangement, and I'm going to get squared, right? I need to square this. Right, because this is k squared. Y'all led me astray. K squared is equal to 2 me over h bar squared. I realized that as soon as I was multiplying over, I was like, where's my n squared? So I'm going to have n pi over L squared is equal to 2 me over h bar squared. A little bit of rearrangement, and I'm going to get n squared pi squared h bar squared over 2m L squared is equal to E. While all of that math may have been relatively unimpressive, right? I mean, all I did was figure out when sine was equal to 0 and then say that those two things must be equal to each other. This result is actually shockingly impressive. This result, I'm going to go ahead and put an E sub n here, knowing that n is equal to 1, 2, 3, 4. This result is the quantization of energy. Energy, because of these boundary conditions and the equation that we're solving, energy is not any value we want. Did I forget something? No, okay. I heard some whispering, I got worried. Energy is going to depend on some counting number, a discrete counting number. Energy is going to be quantized. Has to be. That is the revolution that chapter 7a is all about, is accepting that energy is quantized. They did it for harmonic oscillators, we'll get there eventually, but this is the example for the easier one to calculate. We can also, now that we've got this condition, we can also say what our psi of L is, or psi of x is equal to. That is going to be C sine, sorry, it's going to be a little off the camera, sine n pi over Lx. I like to write it specifically that way, n pi over Lx. This is where that quantization kind of comes from. So we've got a wave function, and we've got some energy. We've got our eigenvalues and our eigenfunctions. And now with this, and since we're in restricted space, now we can start doing all those integrals that you've all been dying to do. So we can start looking at this. Let's see, I want to make sure I'm in the same spot in my notes. Cool. So we have a couple things we can do now. A couple things we should do. First off, we want to realize that the wave functions we found are eigenvalues of the Hamiltonian, but we already know they're not going to be eigenvalues of the momentum. That's going to make it difficult for us to figure out the momentum of the particle. We can't figure out the exact momentum. We can do average momentum. We know that those functions are eigenvalues of the Hamiltonian, but they're not eigenfunctions of position. So we're not going to get eigenvalues for position. We have to do average position. But we can do all of that. We can also go back to the fact that we picked a Hermitian operator, and I could actually put this, sorry, I'm going to call this psi n, because, you know, it's also depending on the counting number. So we've got a couple things we can do. We can show that the psi n is going to give us orthogonal wave functions. If I take psi n and then a psi m, and those two things aren't equal, I should get an integral that's 0. And we can look at that and say whether that's true or not. And then we can start calculating all of those position and momentums, the averages. First thing I want to do is I want to find the probability of the function inside here. So I'm going to say my probability is going to be the integral from 0 to L psi star psi dx. This integral ends up not being that bad. Well, I should bite my tongue a little bit there. Oh, it's because I did it generically. Oh, that was a much bigger problem. And we're going to do this for a psi n psi n. We're going to pick the same function twice. We're going to, and we now, I want to point out, something I forgot to point out. We now have an infinite number of solutions, an infinite number of eigenfunctions we could look at, because n can count all the way up to infinity. I have a whole set of eigenfunctions, what we would call the eigenbasis. It's a set of functions that describe this. If I'm looking at the probability of just the first set, let's not make it more simple. Let's just do psi and psi. I'm going to have the integral. Get ahead of me if you can for doing this integral. Also, if you don't have your integral tables out, you're going to need your integral tables out because I don't have all of those memorized. I'm going to have the integral from 0 to L of c sine n pi over xl. Whoa, I just lied. N pi over Lx times that we're going to take the complex conjugate of times c sine n pi x over L dx. So one of the nice things about using these functions instead of the exponential functions is sines are real. So when I take the complex conjugate, I actually just get the same thing back out. And then I know the c is going to be some constant. I can move that out. I've got c squared, integral from 0 to L, sine n pi x. It's going to give me a sine squared n pi over Lx dx. Now what I need you to do is go ahead and look at your integral table and tell me what the integral of sine squared is. Somebody, help me. Whoa, why did I put x squared? Probability, oh, that's supposed to be c squared. C squared times x over 2.
Minus sine 2ax all over 4.
Sine quantity 2. A in this case is going to be n pi over Lx all over 4 n pi over L on the boundaries from 0 to L. Now, we can do this part kind of on our own, right? Without thinking about it too much. Sine of 0, 0. Sine of n pi, because if I plug in x is equal to L, I'm going to get 2n pi. Whatever n is equal to, sine is equal to. Oh, should I write this down? Too much math in my head? Let me do it in a little different color. I haven't used enough colors in the last 5 minutes. Sine, let's do the upper bound first. Sine of 2n pi L over L. If the L's cancel out, I've got the sine of 2n pi. Sine of 2n pi is equal to 0. If I do the lower bound, I'm going to have sine of 0. Sine of 0 is equal to 0. That whole term goes away. This means my probability is going to be, upper bound is going to be L over 2. So I'm going to have c squared times L over 2 minus 0 over 2 is just 0. My probability is going to be c squared L over 2. Ta-da. Now this was the integral over all space, over our entire boundary. What should be my probability of the particle existing in all of the space that we're considering? 100%, or 1. What we have just done I want to write that in a different color too. This is an important thing. If the probability is equal to 1, then psi is what we call normalized. Right? We've set our total possibility of existence equal to 1. Right? In that case, we would actually call this most books, most texts, most places where you look at quantum mechanics would not call this letter C. Then they would call this capital N for the normalization constant. And you would find that, in this case, I'll leave it as C for now. But we would find, in order for the probability to be equal to 1, we have C is equal to 2 over L to the 1/2. That would now normalize our wave function so that our probability in all of the space we're considering is 100% equal to 1. That means I can now rewrite my wave function a little bit differently. I can change that C to a 2 over L to 1/2. This wave function is now normalized. I want us to prove something else about this wave function. So we can now go ahead and with this normalized wave function, we can find the average position, we can find the average momentum, but I want to prove something else first. Do I want to prove something else first? Let's calculate the average. Yeah, I want to prove this first. The thing I want to prove is that a psi n with another psi n is orthogonal. That restriction that we had using our Hermitian operators said that these functions should be orthogonal to each other. We've now normalized them. If they are also orthogonal to each other, we call it an orthonormal set. So let's go ahead and let's prove that these are orthogonal to each other. That is to say, I'm going to take the integral psi n star psi m dx from 0 to L. And I want to find out what this is equal to, where the n and m are not equal to each other. This is going to be a bit more of a headache than the last one. We've got some ways that we can simplify it, but it's going to be a bit more of a headache. The reason it's going to be a bit more of a headache is, let's go ahead and plug this all in and see how it starts working out. My normalization factor comes out front as a 2L. I'm going to have the integral from 0 to L of sine n pi over Lx. Notice I just dropped the star because I already know this is a real function, so taking the complex conjugate is just going to give me the same thing, times sine m pi over Lx dx. If you look at your integral table for sine ax times sine bx, it's a bit of a mess. I don't really like it. So instead, a question?
Yeah, where did you get the 2 over L from?
That's the normalization factor. The 2L would be out here twice. Sorry, the 2L to the 1/2 is out here twice, and then I just moved it out. 2L to the 1/2 times 2L to the 1/2. That's our normalization factor.
Oh, so we use the normalized.
Yeah, so we're using the normalized wave function. Once we always want to be using normalized wave functions. Normalized wave functions just make it so our answers are more comparable to each other. So, different ways that we can prove that this is true. I find the easiest way to do it, rather than doing it for the generic n and m, is to do it for sine of, let's say, n equals 1, m equals 2, just for some n not equal to m. If we did it where n equals m, we'd just be doing the same normalization integral we already did, and we just get answers equal to 1. Let's do it for not a generic case, but sine of pi over Lx and sine of 2 pi over Lx. This is still going to be a bit of a messy integral, but it's going to be a little bit easier. This is going to be, well, I don't even know if this one's on your integral table now that I think about it. Do you have a sine A, sine B? Oh, okay. That's because for you, I'm going to prove it. I'm going to show you right now. I looked it up earlier. But that's, for us, really, theoretically, we don't need to do this integral, right? Theoretically, we say these are two different eigenfunctions of the same Hermitian operator. And if they're two different eigenfunctions of the same Hermitian operator, we already know this integral is going to be 0. I just want to prove it to you once so you can see where it's useful. Why that's useful. So I'm going to go ahead and I'm going to say I've got my 2 over L. I'm going to have a quantity sine pi over L minus 2 pi over L x divided by 2 pi over L minus 2 pi over L minus sine pi over L plus 2 pi over L x divided by 2 pi over L plus 2 pi over L, evaluated from 0 to L. What a mess. What a mess indeed. The nice thing is we can simplify, since we're not doing it for generic n and L, n and m's, we can simplify these insides a little bit. I can say pi minus L, pi over L minus 2 pi over L is just negative pi over L. Right, so I'm going to go ahead and do that. I'll do it in a different color so you know that I simplified things. This is just going to be a pi over L. That x should be on the inside. Same thing here. Oops, forgot my negative sign. Don't forget your negative signs. Same thing's going to happen here. I'm going to have a pi over L minus 2 pi over L. That should just be a negative pi over L. Same thing happens over here, but a little bit of a different story. This is going to end up being a 3 pi over L. And this one is going to end up being a 3 pi over L. Now, without explicitly doing this, we're just going to talk through it a little bit. If we look at x is equal to 0, we've got sine of 0 minus sine of 0. That's 0 minus 0. That's 0. Everyone good with that? Okay. The L one's a little bit more difficult. Sine of negative pi, 0. Sine of 3 pi, 0. This whole thing, doesn't matter that the 2L is outside, this whole thing is equal to 0. We can now repeat this an infinite number of times if we so desire. We can do it for n equals 1, m equals 3, n equals 1, m equals 4, n equals 2, m equals 3. We can just keep doing this over and over again. However, and I'll repeat this very important feature, because these are eigenfunctions of the same Hermitian operator, they are all orthogonal. Because these are eigenfunctions of the same Hermitian operator, these are all orthogonal. And I'll go ahead and now replace that question mark with equals 0 because ortho. That means we call this set orthonormal. This is going to save us on so many integrals. We're going to have a bunch of integrals that we can just set equal to 1 if it's normalized, or set equal to 0 if it's an orthogonal set. This is going to simplify things for us. Okay. Let's look at, I want to do one more calculation. I think we've got enough time for it because I want us to calculate something that's physically real so we get a sense of why we've been doing all of this. We've got our confined particle. I'm not going to worry about that wave function right now. We've got our confined particle. I want to know, I know the particle's confined here. I can look at my probabilities. I know that they're going to be sign functions. As n increases, I'm going to have different energies, and I'm going to have different wiggliness. We can look at that next time. You can also look at that in the textbook if you're not reading along. You can be. I want to do one more calculation before we finish today. That's the average position of this particle confined to the box. So that way we could get something that's actually physically measurable. Where is this particle? We should be able to think about this just from a rational standpoint, but quantum mechanics isn't necessarily rational to us yet. So let's just do the integral. Let's solve the problem. I'm going to have the integral from 0 to L. And I'm just going to do this for the n equals 1 case. I'm going to have psi 1 star times psi 1 dx. Oh, I forgot something if I'm doing average position. Got to have my x operator. X hat psi 1 dx. The x hat operator is really just multiplied by x. So I've got that. I'm going to go ahead and plug in all of the functions that we have, all of the things we know. Integral 0 to L, I'm going to have my 2 over L to the 1/2 sine pi over L x times x times 2 over L to the 1/2 sine pi over Lx. Collecting terms, simplifying things, getting it so it's an integral someplace on your integral table. We're going to have 2 over L, bringing those two L's together. Integral 0 over L x sine squared pi over Lx dx. I forgot my dx over here. Don't forget your dx. This should also be an integral someplace on your integral table. I'm not saying it's necessarily a pretty integral, but it should be someplace on your integral table. Someone who's got that handy, holler it out to me, or speak it nicely either way. What is x sine squared pi L over x dx? What is that integral?
X squared over 4.
X squared over 4
Minus sine 2ax.
minus 2. That's going to be pi over Lx
4a. So 4
divided by 4 pi over L. Are we done?
Oh, there's a
No.
sorry. There's an x in front of the sine 2ax. Yeah.
X. Okay. Okay.
Minus,
And then, oh, geez, there's more?
yeah,
Minus
cosine 2ax.
cosine 2 pi over Lx
Over 8a squared.
over 8
Squared.
pi over L squared. Evaluated from 0 to L. That is a whole lot of terms. For this number of terms, I'm actually going to do the evaluation of each term. I'm going to do them backwards from the order I have them written down, though, because the cosine, the cosine and sine terms are a little bit easier to deal with. Let's just do it. Let's just do it. So I'm doing this thing here. Okay, so I've got my 2L. I'm going to have L squared over 4 minus 0. That part's easy. Then I'm going to have minus L sine 2 pi over L divided by 4 pi over L. What's that equal to? Particularly, what's this equal to? Sine of 2 pi.
0.
0. Great. Minus, I've got to do the 0 one as well. I'm going to do this, 0. X is out front, so it's going to be minus 0. So this thing is also equal to 0. Then I'm going to go ahead and do the cosine term. I'm going to have minus cosine 2 pi over L over, I'm just going to leave this, we can just leave this, 8 pi over L squared. So that's the L term. Minus cosine of 0 over 8 pi over L squared. Cosine of 2 pi, cosine of 0, 1 minus 1, 0. That whole thing goes to 0. Those two things together also goes to 0. Our answer for the average position is going to be 2L times L squared over 4, 2 over L times L squared over 4, L over 2. What this means in terms of the particle in the box is the average position is in the middle of the box. Our average position is in the middle of the box. Now, in terms of what we're going to be doing in this class, there will be times when I'm asking you to calculate expectation values and do these integrals. Notice, though, by being comfortable with sines, cosines, exponents, a lot of times things go to 0. We get a lot of places where things just collapse to 0. So we want to be keeping our eyes out for that. Another thing, I want to mention this before I forget, another place that's going to make our lives easy doesn't happen in the particle in a box, but we always want to look for even integrals and odd integrals over even and odd bounds. If we have an odd integral over even bounds, it's equal to? Oh, do you guys remember that? I'm getting not much. Okay.
Can we just shout out 0 because it's a magic?
Shout out 0. 0. If we've got an odd integral over even boundaries, over symmetric boundaries, it's a 0 integral. Right? We just end up with 0. So there's going to be these situations where things keep canceling to 0. We're going to be using our orthonormality to get integrals that are equal to 0. We can use even and odd integrals, and I'll go over this again at the beginning of class when we do the, if actually we could have done even and odd integrals here. Sine is a even or odd function? Odd function. Odd function times an odd function is even. X is an odd function. This is an integral of an odd function. Oh, wait. Oh, the boundaries aren't even. The boundaries aren't symmetric. I freaked myself out for a second. I was thinking of another problem. I was thinking of a homework problem I'm giving you. Sorry. So this one, because the boundaries aren't symmetric, you don't end up with 0. There's a trick we can do. I'm putting this on. I'm making a homework assignment for you that's not just problems out of the textbook. And I have us shift this so you end up with symmetric boundaries. And it makes all the integrals, it makes the integrals so much easier to do, because we can just use even and odd integrals. If that's all, I got a lot of blank stares at even and odd integrals. So we'll talk about that. We're almost out of time, so we'll talk about that at the beginning of class next time. But even recognizing integrals as even and odd or symmetric or anti-symmetric is going to be another place where we get to simplify our integrals a lot. We're not done yet. I want to leave, I'm going to always try to leave the last 5 minutes so you can ask me questions. Questions, yes?
Very last term, I just wanted to add it. Cosine 0 is 8 pi over L squared.
Yeah.
Is it that entire term
It's this whole thing because we've got essentially we can
So 1
factor
minus
out that we've got 1 minus 1, right? So we've got 1 over 8 pi over L squared minus 1 over 8 pi over L squared. We end up with a 1 minus 1. Other questions? Okay, so this gets us pretty deep into chapter 7D. If you haven't been reading along, what we're going to do next time is we're going to look at some more integrals. We're going to look at the x squared. We're going to say, we're going to look at the probability distributions inside the particle in a box. And we're going to start talking about how we can look at the average and we can look at the deviation from the average. And we're going to start looking at how we can look at that deviation of the average. That is going to allow us to calculate and essentially derive the Heisenberg's uncertainty principle from just mathematics rather than being like, oh, it's a thing. We're actually going to derive the Heisenberg's uncertainty principle by looking at our deviation in terms of position and our deviation in terms of momentum. If there are no other questions, we're ending a little bit early. I'm going to encourage you to spend the next 3 minutes talking to the people next to you, see what questions they have that you can answer or what questions you have they can answer. Make sure you leave this room feeling like you understood everything we did. Because today, the things we did today are essentially what we're doing for the rest of the quarter. Okay.